Can I begin?
All right. Welcome, everyone. This is the session for computational methods, tools, and thermal fluid systems, second one in parallel sessions. We have our first speaker here ready, Christina Aintablian. She's a student from Liberty University.
Yes.
You can start.
All right. Hello, my name is Christina Aintablian, and I'm presenting my undergraduate research on the optimization of Wordle gameplay strategy. If you've never played a game of Wordle, when you open the game, you're presented with this grid of rows. The objective of this game is to guess the 5-letter word of the day in under 6 guesses. Each of these rows corresponds to one guess of a 5-letter word. So let's say your first word you input is water. You see that each of these letters are gray, meaning that none of these letters are present in the word of the day. So you put in a second guess. Hydro. You see the D in the middle is yellow. That means that there is a D in the word. It's just not in that column. So you try another word, and it's the same thing with the I. The letter is in the word, but it's not in that location. You try one more guess, and you see that the F and the L are both green, meaning that these two letters are in the right location and they do exist within the word of the day. You try one more guess, and you see that all the letters are green, meaning that you've successfully guessed the word of the day in under 6 tries. There are over 12,000 words, 5-letter words, in the English language. However, Wordle picks from a set of just 2,300 of them. This set was designed to exclude the unfamiliar, vulgar, political, plural, and past tense words, thereby decreasing the difficulty of the game. Because of this difference in sets, the letter statistics may differ. These include the total probability of letter occurrences, positional dependencies of letters within the word, and joint probabilities of letters occurring together. Additionally, the word of the day is chosen by Tracy Bennett from Maine, usually 6 weeks in advance of the game. Because of this, there is a human factor incorporated into the string of words used by Wordle. Tracy intends to, with her answers, avoid repeated letters and linguistic structures day to day, thereby avoiding patterns that would make it easier to guess the word of the day. The goal for this research project is to develop a system that would help determine the best 2 guesses to begin a Wordle game with in order to guess the word of the day in the least amount of tries. This system would incorporate a dependency on recent history, so including Tracy's bias in her past answers, and incorporate linguistic data. A brief history on introduction to Shannon entropy. Shannon entropy defines information as a measurable value. It's a higher entropy event is something that provides more information when it occurs. And conversely, a lower entropy event provides less entropy when it occurs. Surprisal is information from a singular source. When an event that has a low probability of occurs, that tells you a lot about the system, thereby providing a significant amount of information about that system. Conversely, when a high probability event happens, we already know it's going to happen. So when it happens, you're not surprised. And that tells you little about the event and the system that causes it. It's calculated by this equation. Note the log base 2 structure of the equation. The entropy of an event is the expected value of all the information sources. It's effectively a weighted average of all the surprisal terms. Entropy is measured in bits. This leans back to the log base 2 structure. When you receive 1 bit of information, this splits your set of all possible outcomes in half, meaning that only half of the original outcomes can continue to occur. While if you receive 3 bits of information, that means that there's only 1/8 of the original set of possible outcomes remaining that can occur. And finally, entropy. Joint entropy is additive, so if you have 2 sources of entropy, you can add them together and get the total entropy of 2 items. See here that there's a conditional probability matrix that conditions the rows, the columns by the rows. So Conditional probabilities are really helpful to lower your set of possible outcomes if you have information about the answer already. So it's helpful specifically in regards to Wordle. When you've received information on your first guess, you can condition possible values that may occur based off of information you've already received. So if you know that there is a D in your letter, you can condition your remaining answers given that there is a D already. Um, so that's really helpful to narrow your remaining set of possible outcomes. Additionally, there is the vowel distribution, positional distribution within the word. You can see that there are very similar distributions between the non-E values. This indicates that the non-E vowels are less likely to occur together because they favor similar locations within the word. Meanwhile, E favors the second half of the word. Um, this means that it's more likely for a non-E value to occur with E. You can see this pattern in words like chore, crate, great, where there is a vowel, a consonant, and a vowel. And this is called the vowel consonant vowel pattern in linguistics. These are the kinds of things that Tracy avoids repeating in adjacent answers. You can see here that there is the consonant letter distribution for a few of the most popular consonants in Wordle. You can see that there is a less consistent distribution of consonants. But in the middle, you can see that there is a dip in the probability of occurrences. This implies that vowels are more likely to occur in the middle of the word. This is called the consonant vowel consonant structure. Repeats of these are also things that Tracy likes to avoid. Based on these sources of information, we can determine the highest entropy words that we should be starting our Wordle game with. Words like tears, salad, orate, rates, tears, and nares. These include the most popular vowels like A and E and a range of the most popular consonants. And these words put these letters in the locations of the word where they are most likely to occur so that we can receive the most green and yellow letters from these words. The methods I followed included a 5-step process. The first was to calculate the probability of each word. I did this assuming independence between letter occurrences. The second was to choose a first guess. I chose quiet because it had a very low probability letter, Q, and several high probability letters. And this would be interesting to see if my methods would produce the results that I expected from it, which we will see later. And the third thing I did was for every combination of letters in the guess, I created a separate set of words containing it. So for example, from the original set of about 1,200 words, I would create a separate set that just had a Q or a U, or a Q or an I, or a Q, U, and I, and so on for every possible combination of letters. And then I computed the total probability of each set by summing the probabilities of each word. And then I calculated the expected value of entropy for each of these guesses using the equations on the previous slides. And then I calculated the distribution characteristics of each guess, which would tell us how good each guess was. The first word I used, I actually tested was salad because of its high entropy. It produced 8.1 bits of entropy relative to the maximum entropy of 11.79 bits, which seems high, but that is only because my model did not take into account the positional dependence of letters. It had a standard deviation of probabilities that was quite low, in addition to a Gini coefficient of 0.09. These indicate that the entropy due to each letter was relatively even. There wasn't one letter that contributed more to the total entropy of total expected entropy value than others, meaning that salad is a very good word to begin a guess with. Meanwhile, quiet also produced a high entropy, but it had a relatively low standard deviation. However, it did have a high Gini coefficient. This is because Q is a low probability letter, meaning that it contributed significantly less to the expected value of the entropy than all the others. So effectively, it's a wasted letter. It would be much better to put something else instead of Q there. So quiet, that indicates that quiet's a rather poor guess to begin a game with. I chose to use gnome as my second guess, my third guess, because of its linguistic structure. It has a silent G there, which is another thing that Tracy would be incorporating into her guess selection. It had a little bit of a lower entropy, um, and it had a little bit of a higher standard deviation and a moderate Gini coefficient. It's a fine word. It has two vowels and it has a relatively high occurring consonant, but the G and the M are neither of which are significant letters that occur too frequently. And the final word that I tested was whack. It had definitely the lowest entropy of all the words that I tested, and a bit of a higher standard deviation and a moderate Gini coefficient. Um, there are two very low probability letters here in this word, the W and the K, both of which occur very infrequently. But the Gini coefficient is still low because the total distribution of words that create the entropy is more even. So there are two low probability letters in here instead of just one in quiet. As you can see also, things that we look for in this sorted PMF is a longer, thicker tail, which occurred in the words salad and quiet. Here in whack, we have a much shorter, much thinner tail. This indicates that there are less words that have a lower probability of occurring, which creates the lower entropy value in this word. So the conclusions of this project were that we determined the entropy distribution of guesses by calculating the expected value of the letters. The information of each of the words is dependent on the probabilities of individual letters. Silent and quiet were both both had high expected entropy values, which was expected based off of the probability of the letters occurring that were in the words. And therefore, they're better exploratory guesses. They're better to use to begin a game of Wordle with. Meanwhile, gnome and whack both had lower expected entropy values, but they were biased towards a certain subset of linguistic patterns. They both contain silent letters, and whack has the CK, which are two letters that very frequently occur together. So they both follow structures that Tracy Bennett is more likely to include in her selection of answers. Oh. And finally, we've laid the fundamental groundwork to proceed with a time-dependent model to predict the expected entropy values of Wordle guesses. And so future steps, future plans achieved at Wordle is first to validate the entropy calculations that I've presented, prove that they are correct and there aren't errors in them, to identify patterns in word appearances. So these are the things that Tracy will be doing. I've previously attempted this. I was unsuccessful because there was, on day 400, there was a switch from Wordle's method of selecting answers. It was originally computer automated and it switched to being chosen by a human editor, Tracy Bennett. Unfortunately, those first 400 days were in my data set, and I was not aware of this until just about a week ago. So that significantly skewed my attempts to identify patterns in the Wordle appearances. There was a detectable shift in the data around after day 400. Additionally, we know that Tracy Bennett was the editor. She's from Maine and usually chooses her words 6 weeks in advance. She now lives in New York. I am planning to attempt to identify her bias in selecting words by accounting for silent letters, phonetics, various linguistic structures like the ones that we've heard before, in addition to letters that are more frequently to occur together. In addition to her biases and word familiarity that I intend to locate by counting word appearances in popular media from both Maine, New York, and anything else that she's written. Um, yeah, quantifying word familiarity counts in popular media, and then using applications from computational linguistics to complete this project. And then if there are patterns that exist, I will then weight the entropy calculations based off of the previous day's answers in order to create a more accurate model for future days. Any questions?
Thank you. Do we have any questions?
Yes.
So, just a curiosity question. So, something like a word which has a lot of vowels, like audio.
Yeah.
What do you expect it to happen?
Definitely very high because there's almost always vowels in the word. There have been a few words that only had Y's in them, but like those are like, I want to say that there's only been like one or two of those. So definitely very, very high, especially because R is, I believe it's the most, either the most or the second most frequently occurring letter. So that is very high. From the literature that I've seen, it's definitely rated like as up there.
So going on that, would audio be a good word since it doesn't really narrow your search down? It just has a lot of letters that are in a lot of words.
Yeah, it still gives you information. It really depends. In those cases, it really depends on whether or not you're going to get the green letters or the yellow letters, because just telling you that a letter is present in your word doesn't exactly tell you too much, but it does give you information. If you get green letters, that tells you a lot. Now, because you have a D in your word instead of an R, that's, if there is a D in your word, that tells you more, because D is not exactly one of the more frequently occurring letters. If that makes sense, yeah.
So do you recommend starting with that?
With audio, I mean,
because when you said it was high, I don't know if that meant high probability of starting. Yeah.
it's a higher entropy word. I don't think I would recommend audio specifically, just because it's mostly vowels. I would recommend salet, orate, words that have a few more consonants, just because it tells you a bit more. Yeah.
What does the model do, or what's Wordle do if it has a word that has a double vowel, such as goofy? Like the word goofy, I was just thinking, originally I was thinking like goose, but then like, oh, that's sorry.
Well, I don't know if, well, when, okay, in order to get like, for it to tell you that there's a double letter, you have to guess a word with that double letter. So like you have to guess like food, and it'll turn up with like two green letters, if that makes sense. You know what I mean?
Would you recommend starting with that column?
Not with a double letter. No.
Because it costs a whole.
Yeah, it's a waste of a letter.
This was a great, very much of a freshen up of the day. Beautiful presentation. Let's thank our So our next speaker